Let's say that when I have some object, and when it's outside of water, its weight is so weight outside of water is, I don't know, 10 newtons. And let's say when I submerge it in water, I put it on a weighing machine in water, its weight, so let's call it weight in water, is, I don't know, it's 2 newtons. So what must be going on here? Well, the water must be exerting some type of upward force to counteract at least 8 newtons of the person's original, not the person, the object's original weight. This would be a very small person. Most people's weights in newtons are in the hundreds. But anyway, and that difference is the buoyant force, right? So a way to think about it is once you put the object in the water, so let's say it's it could be a cube. It doesn't have to be a cube, it could be anything. And it's in the water. So let me draw the water. This is the water up here. We know that we have there's a downward weight, right? That is 10 newtons. But we know that once it's in the water, the net weight is 2 newtons. So there must be some force acting upwards on the object of 8 newtons, right? And that's the buoyant force that we learned about in the previous video, and the video about Archimedes' principle. This is the buoyant force. So the buoyant force is equal to 10 minus 2 is equal to 8, right? That's how much the water is pushing up. And what is that also equal to? That equals the volume, the weight of the water displaced. So 8 newtons is equal to weight of water displaced. And what is the weight of the water displaced? That's the volume of the water displaced times the density of water times gravity, right? And so what is the volume of water displaced? Well, it's just the volume of water, divide 8 newtons by the density of water is 1,000 kilograms per meter cubed. Right, this is 8 newtons. So a newton is what? Kilogram meter per second squared. And then what's gravity? It's 9.8 meter per second squared. And if we look at all the units, they actually do turn out with just, you end up having just meters cubed. But let's do the math. So we get, let me get my calculator. So I have 8 divided by 1,000 divided by 9.8 is equal to 8.2 times 10 to the negative 4 equals 8.2 times 10 to the minus 4 meters, cubic meters. So just knowing the difference in the weight of an object, I can figure out the difference when I put it in water. I can figure out the volume. And so this could be a fun game to do next time your friends come over, is weigh yourself outside of water, then get some type of spring or waterproof weighing machine, put it at the bottom of your pool, stand on it, and figure out what your weight is, assuming that you're dense enough to go all the way into the water. But you could figure out somehow your weight in water, and then you would know your volume. And there's other ways. You could just figure out how much the surface of the water increases and take that water away. But anyway, this was interesting. Just knowing how much the buoyant force of the water was, or how much lighter we are when the object goes into the water, we can figure out the volume of the object. And this might seem like a very small volume, but just keep in mind, in a meter cubed, you have, let's see, you have 27 square feet, right? You have 27 square feet. So if we multiply that number times 27, it equals 0.02 square feet, roughly. And 0.02 square feet, how many, in a square foot, there's actually, let's see, 12 to the third power times 12 times 12 is equal to 1728 times 0.02. So this is actually 34 square inches. So the object isn't as small as you may have thought it to be. It's actually, it's like maybe a little bit bigger than 3 inches by 3 inches by 3 inches. So it's a reasonably sized object. Anyway, let's do another problem. Let's say I have some balsa wood, and I know that the density of balsa wood is 130 kilograms per meter cubed. That's the density of balsa wood. And I have some, big cube of balsa wood. And what I want to know is, if I put that, so let me draw the water. That's the water. And I have some big cube of balsa wood, which I'll do in brown. So I have that big cube of balsa wood, and the water should go on top of it, just so you see that it's submerged in the water. All right. I want to know what percentage of the cube goes below the surface of the water. Interesting question. So how do we do that? Well, for the object to be at rest, for this big cube to be at rest, there must be zero net forces on this object, right? So in that situation, the buoyant force must completely equal the weight, or the force of gravity. Well, what's the force of gravity going to be? Well, the force of gravity is just the weight of the object, and that's the volume of, let's just say, the wood, volume of the balsa wood, times the density of the balsa wood, times the density of balsa wood, times gravity. And what's the buoyant force? The buoyant force is equal to the volume of the displaced water, right? Volume of displaced water. But that's also, well, it's the volume of displaced water, and it's the volume of the cube that's been submerged. The part of the cube that's submerged, that's volume, that's also equal to the amount of volume of water displaced, right? So we could say that's the volume of the block submerged, which is the same thing, remember, as the volume of the water displaced, times the density of water, times gravity. Remember, this is density of water. So remember, the buoyant force is just equal to the weight of the water displaced, and that's just the volume of the water displaced times the density of water times gravity. And of course, the volume of the water displaced is the exact same thing as the volume of the block that's actually submerged. And since the block is stationary, it's not accelerating upwards or downwards, we know that these two quantities must equal each other. So V, volume of the wood, the entire volume, not just the amount that's submerged, times the density of the wood times gravity, must equal the volume of the wood submerged, which is equal to the volume of the water displaced, times the density of water times gravity. Well, we have the acceleration of gravity. We have that on both sides, so we can cross it out. Let me switch colors to ease the monotony. And then let's see what happens if we divide both sides by the volume of the balsa wood. You get, let's put this over here. So you get, well, let's divide both. Well, I'm just rearranging this equation. I think you'll figure it out. We can divide both sides by that. You get the volume submerged divided by the volume of the balsa wood, right? I just divided both sides by VB and switch sides is equal to, is equal to the density of the balsa wood divided by the density of water. That makes sense? I just did a couple of quick algebraic operations, but hopefully that, get rid of the G, and that should make sense to you. And now we're ready to solve our problem. Because my original question is, what percentage of the object is submerged? And so that's exactly this number, right? If we say this is the volume submerged over the total volume, this is the percent submerged. And so that equals the density of balsa wood, which is 130 kilograms per meter cubed, divided by the density of water, which is 1,000 kilograms per meter cubed. So 130 divided by 1,000 is 0.13. So Vs over Vb is equal to 0.13, which is the same thing as 13%. So exactly 13% of this object of this balsa wood block will be submerged into the water. That's pretty neat to me. And it actually didn't have to be a block. It could have been shaped like a horse. I'll see you in the next video.